Hello, this is Mr. Lee's physics class. I'm Mr. Lee. Solid, liquid, and gas are the three states of matters. In this video, we will talk more about the change of state among them. The process of a solid changing to a liquid is called melting, also commonly called fusion. For a pure substance, fusion happens at a specific temperature called the melting point of the substance. The reverse process, that is changing from a liquid back to a solid, is called freezing, also commonly called solidification. And this, for a pure substance, again happens at a specific temperature, this time called the freezing point. Note that for a pure substance, its melting point is the same as its freezing point. I hope you find this sensible. After all, what's the meaning of the melting point of a pure substance? It means heating up a substance across this temperature, it turns from a solid to a liquid. So, higher than this temperature is a liquid, lower than this is a solid. That is to say, if you cool it down across this temperature, it changes from a liquid back to a solid. Well, then this is the freezing point, isn't it? So, for a pure substance, its melting point must also be its freezing point. Take water as an example. 0 degrees Celsius is its melting point as well as its freezing point. Heating up ice across 0 degrees Celsius melts it to water, while cooling down water across 0 degrees Celsius freezes it to ice. While everything by far sounds so reasonable, here comes two big questions. First, what's the state of a substance at its melting point? Second, if a substance melts and freezes at the same temperature, how do I know at this temperature whether it's melting or freezing? Water as an example again. In what state is water at 0 degrees Celsius? Is it melting or freezing at 0 degrees Celsius? To answer this, you need to know how heat is transferred during melting and freezing. Let's use common sense again. To melt ice into liquid, do you keep heating it or cooling it? Of course, you have to keep heating ice to melt it. That is to say, heat is absorbed by ice for it to melt into water. This turns out to be general. All solid substances have to absorb heat for them to melt. The amount of heat absorbed by a solid in order for the entire solid to melt completely is called the latent heat of fusion. To have a clearer picture, let's consider ice again. Suppose this picture shows a piece of pure ice initially at -10 degrees Celsius. It is placed on a heating plate. As you heat it, its temperature increases, but as long as it is still below its melting point, 0 degrees Celsius in this case, it's still completely solid. But at the moment its temperature achieves 0 degrees Celsius, melting starts. Let's say its latent heat of fusion is 5,000 joule, then starting from this moment, it has to absorb 5,000 joule for the entire piece of solid to melt completely. Then, when you have provided, say, 500 joule of heat to it, that is 1/10 of its latent heat of fusion, then 1/10 of its mass will have been melted to water. When it has absorbed 4,000 joule of heat, that is 4/5 of the latent heat of fusion, then 4/5 of the original mass will have been melted. When it has finally absorbed all the latent heat of fusion it needs, that is 5,000 joule in this example, it melts completely. While I used water and ice as an example just now, the discussion above applies to the melting of all pure substances. Now, let's get back to my two questions. Number one, during melting of a substance, what's its state? Well, you have already witnessed the answer. As shown here, when it's melting, it's a mixture of solid and liquid. Another way to say it is that the solid and the liquid coexist. Note that when it is melting, the part which is not yet melted remains at its melting point. In our example of ice and water here, the not yet melted ice remains at 0 degrees Celsius. Of course, this should be it. If it was higher than 0 degrees Celsius, it would already be liquid water but not ice. So, the melting solid must remain at its melting point throughout the entire melting process no matter how strong you heat it. Now, assuming that the solid part and the melted liquid part are in thermal equilibrium, the liquid then should be at the same temperature as the solid, that is, also at its melting point, 0 degrees Celsius in this example. This has profound implication because it means that as long as the solid hasn't yet all melted, the temperature of the melted liquid part always remains at the melting point even if you keep heating it. Then, when can the liquid rise in temperature? Well, you will have to keep heating the solid liquid mixture until all the solid has melted into liquid, and then you don't stop, you go on to heat it, then the temperature of the liquid will rise. In short, as long as the melting of the solid hasn't yet completed, the liquid and the solid both remains at the melting point. The temperature can only rise after all solid has melted to a liquid. Then, what about freezing or solidification? While latent heat of fusion is absorbed by a solid at its melting point in order for it to completely melt, if the same amount of liquid is to freeze back to solid, it will release back this same amount of heat to the surrounding. So, the latent heat of fusion of a body is on the one hand the heat absorbed by it in solid state to melt completely, but on the other hand also the heat released by it in liquid state to completely freeze. One more thing about the solidification of pure liquid. As I said, the temperature of a pure substance during melting remains constant at its melting point. Similarly, the temperature of a pure substance during freezing also remains constant at its freezing point. But I also argued that the melting point and the freezing point of a pure substance is the same temperature. So, to sum up, the temperature of a pure substance during melting and during freezing always remains constant at the melting point. The temperature can change only after the pure solid has been completely melted or after the pure liquid has been completely frozen. This gets us back to the second question raised previously. When a substance is at its melting point, which is also its freezing point, how do I know if it is melting or freezing? The answer is actually hidden in what I just taught shown here. I'll leave you a hint but let you think about the answer. The hint is that for something to melt, latent heat of fusion has to be absorbed by the substance, while for it to freeze, it has to release the latent heat of fusion back to the surrounding. So, think about it. After melting a solid completely to liquid, if you go on to heat it, the liquid temperature rises. And when it achieves a certain temperature called the boiling point, the liquid will start to boil, that is, change to gas state. This change of state from liquid to gas at its boiling point is called boiling. The term boiling is often confused with the term vaporization, which also refers to the change of state from liquid to gas. In simple terms, boiling is one kind of vaporization. For now, I'm not discussing the details about their difference. I will talk more about this in the future videos. Just like melting, for a liquid substance to boil, it has to absorb latent heat, this time called the latent heat of vaporization. Similar to that, the temperature of a pure solid does not rise during melting. The temperature of a pure liquid does not rise during boiling as well. It stays at its boiling point even if you keep heating the boiling liquid. The temperature can only go on to rise when the liquid has boiled to gas. The reverse process, that is, changing from gas to liquid, is called condensation. Using it as a verb, we can say a gas condenses to a liquid state. While the latent heat of vaporization is the amount of heat absorbed by a liquid for it to boil, the same mass of the gas would release the same amount of latent heat of vaporization when it condenses back to a liquid.